Okay, today we're going to be talking about something called power functions. And in the last lesson, we talked about polynomial functions. But essentially, a power function is very simple. First of all, a power function is a function that is only one single term. That's the first thing. One single term. In other words, it can't have a term plus something else, minus something else. One single term. And the second thing is that it has to have x as its base, or a variable as its base. It may not always be x. And it has to have an exponent. The exponent can be any number. It does not have to be an integer. It does not have to be a fraction. It can be any number. So if you have these three situations, one single term, x or some variable as the base, raised to a numerical power, that is called a power function. Let's look at some examples of power functions that you may be very familiar with. Let's say we have the circumference of a circle. That's equal to 2 pi r. Well, you have to ask, okay, what is the variable? The variable is r. r is raised to the first power. This is a single term. It's not adding or subtracting anything. So if it is a power function, you will say that the constant of variation is just the number in front, so that's 2 pi, and the degree is going to be 1, or the power is going to be 1. Look at another one. We have the area of a circle. So area is equal to pi r squared. We have the variable r being raised to a numerical exponent. So it is a power function. It's one single term. So the constant of variation is going to be pi. And by the way, the constant of variation is everything that's in front of the variable. I'm going to go over that in just a second. The power is 2. All right. Force is equal to K divided by D squared. That can be written as K times D to the negative 2. D is the variable, negative 2 is the power, and K is the constant of variation. So this is a power function. So the constant of variation is K, and the power is negative 2. Remember that anytime you have something on the bottom, you can move it up to the top and make the power a negative power or change the sign. Now, let's say I clear all that out. Let's say that I give you this function, f of q equals a, b, c, dog, cat, q. Now, f of q means q is the only variable in this equation. All right? Even though there's lots of letters, there's only one variable q. So that means that everything other than q, which is all of that, that's going to be your constant of variation. So that's going to be your constant of variation. And the power is going to be q to the first, so the power is simply going to be 1. All right? So these power functions can either vary inversely or directly. If they vary directly, that means you need to do k times whatever the equation is. If it varies inversely, it's going to be k divided by whatever the function is. So this is direct variation, and this, k divided by, is indirect, or actually inversely proportional. Now, the only time that you will ever see inversely proportional is if it says it in the problem inversely proportional. If it does not use this word, you will assume it is direct variation all the time. The only time you'll assume it's inversely is if it says it's inverse. All right, let's see how this works on a couple problems. Okay, writing a power function formula. These can be very, very easy. All you have to do is write it the way it is written. T is varying. Now, it doesn't say inversely, so therefore you have the liberty to say directly. T is varying directly as the square root of the pendulum's length L. Now, please don't confuse square root with squaring. All right, square root is square root. So you will write T equals K times, you need a K, you need some constant, and because it's directly, it'll be K times the square root of L. Very easy to write. Let's see if we can do part B. Q varies, here it is, inversely as the square, not the square root, of P. So you will write Q equals K divided by P squared. Let's read that. Q, there's Q, inversely K divided by the square of P, P squared. Okay, let's do letter C. J varies directly because it doesn't say inversely. You'll assume it's directly. So it's going to be K times the cube of B, so B cubed. And that's all there is really to writing a power function formula. Okay, let's talk a little bit about what is called a monomial function. A monomial function is a single-term polynomial function. All right, it is also a power function, but not all power functions are clearly monomial functions. So, let's make sure we remember what has to be true in order for something to be a polynomial. Well, for it to be a polynomial, the exponent must be a a non-negative integer. All right? And so that's the rules for polynomials. If you have a single term polynomial, that's called a monomial function. So let me give you some examples. Y equals 10x squared. That has one term. It is a power function, but it is also a monomial function because the exponent is a non-negative integer. Now let me give you an example of one that is a power function, but is not a polynomial. Y is equal to 10 divided by x squared, which can be written as 10 times x to the negative 2. Power function? Yes, it is. Polynomial or monomial function? No, it's not, because the exponent is not a non-negative number, even though it is an integer. So, once again, a single term polynomial is called a monomial function. Okay, now we're going to actually work on how to graph these power functions. And a power function, once again, is a function that can be written in the following form. You have some constant k times x to the k times x to the a. All right? So, we want to make sure we understand what each of these letters control. The letter K controls whether it's going to be in the first quadrant or the fourth quadrant. If K is positive, you will draw the graph in the first quadrant. If K is negative, you will draw the graph in the fourth quadrant. Now the letter A controls what type of function it's going to resemble. So let's look at this. If A is equal to 1, then it's going to resemble a linear function. Think about it. K times x to the first is just a linear function. So it's going to resemble a linear function. If A, so let's just write that down. It's going to be linear. If A is greater than 1, like x squared, x cubed, x to the fourth, x to the fifth, those are all going to resemble a parabola. It's going to all have the parabola shape. So the linear will be like that, parabola will be like that. And then if A is between 0 and 1, well, let's just say we have y equals 3x to the 1/2. That's the same as 3 square root of x. So any exponent between 0 and 1 is going to resemble a square root curve. And then the last one is if a is less than 0. So let's say I have y equals 3 over x squared. All right, that's really written 3x to the negative 2. We know that this is a reciprocal function, so it's going to look like either that or that, similar to your reciprocal function. So all four of these are your parent functions that you had to memorize in section 1.3. Okay, let's say we have these three power functions that we are trying to sketch. Well, the first thing we want to do is we want to look at the coefficient that's in front of the power function, and if it's positive, we know we're going to be in the first quadrant. If it's negative, we know we'll be in the fourth. This is positive, so we'll be in the first quadrant. Then we recognize that the exponent, we'll call that a, is less than 0, which means it's going to resemble a reciprocal function. And there is the sketch. Now, you look at the exponent, and if it is an odd number, then you draw the other half with odd symmetry. If it was an even number, then you would make it with even symmetry. Let's look at letter B. Okay, we see that we have negative 0.4. The coefficient is negative. The constant of variation is negative, so we're going to be in the fourth quadrant. And we see that the exponent is greater than 1. So that means it's going to resemble a parabola. So we have a fourth quadrant parabola. So let's go ahead and draw that fourth quadrant parabola. Now the question becomes, what type of symmetry, if any, does it have? Well, in order to figure this out, we need to rewrite this as x to the 3/2 power. And we're going to now say this is the inside power divided by the outside power. And that's how you deal with these fractional exponents. Inside divided by outside. So it's going to be the square root of x cubed. All right, so let's see if it has any symmetry at all. All right, if I plug in, let's say 2 to the third is 8. The square root of 8 is some number. But if I try to plug in negative 2, I get negative 8. I cannot take the square root of a negative number, so therefore this does not have another side to it. It does not have symmetry. All right, let's take a look at this third example here. We have a negative coefficient, so that means we're going to be in the fourth quadrant again. We have let's just say we have a, which is our exponent, and that is between 0 and 1. So that's going to resemble your square root curve. So we are going to be in the fourth quadrant square root curve. So square root curve, fourth quadrant. All right, so let's see if it has any type of symmetry. So we're going to rewrite this as negative x to the 2/5. 2/5 is the same as 0.4 as a fraction. Inside power over outside power. So it's going to be negative. The outside power is going to be the 5th root of x squared. Now, notice, if I plug in a 2 and square it, I get 4. If I plug in a negative 2 and square it, I still get 4. So that means that this has even symmetry because whether I plug in the positive x or the negative x, I get the same answer. So that means this is going to have even symmetry. I'm going to draw the other side in the other quadrant.